Welcome to the Moldex3D Advanced Tips and Tricks. My name is Alex Baker, and today we'll be going over warpage analysis and visualization. Some subtopics you can look forward to are explaining the 6 main causes of warpage, discussing how to run warpage simulation accurately in Moldex3D Studio, and visualizing the warpage in Moldex3D Studio with some advanced tips at the end. All right, so let's first go over what are the main causes of warpage. We call it the 6 main causes. So there's 6 main causes to warpage in simulation. Ultimately, warpage in Moldex 3D is a change in volumetric shrinkage. So if we were able to get our part to just shrink uniformly, then we wouldn't have any warpage. We'd be able to get exactly the same part out of the mold as the geometry that's cut into the mold, just a little bit smaller, because the material will always tend to shrink. But because of certain factors, that shrinkage is going to be non-uniform, and that's really where the warpage comes from. And the 6 main causes of this are part design, mold design, process conditions, the PVT relationship, fiber orientation, and residual stress. So let's dive into those 6 causes a little bit deeper. Starting with part design, the thickness distribution will always influence how the part cools and will ultimately influence the shrinkage distribution. So if I have a thick region on my part, it's going to take longer to cool down than maybe a thinner region on my part. And because the temperature distribution is going to be different between those different regions, the internal volumetric shrinkage is going to be much different and cause it to shrink at different rates. So that sort of volumetric shrinkage variance is where this warpage is going to come from, and that's the common theme. Is if we have a variance in shrinkage, warpage is always going to be apparent. Wall angle also influences where the heat is trapped in the mold. So when we're looking at a cooling system or how the part is able to dissipate from the plastic out to our metal mold base and ultimately out to our cooling system, the angle at which walls come together can actually influence where we're able to extract heat efficiently. For instance, if we have 2 walls that come to a 90-degree angle, it's actually very difficult to efficiently extract the heat from those regions. And that's why you very commonly see fillets and chamfers and other types of geometry that will allow the connection between 2 walls or 2 surfaces to be not abrupt. You don't really want those walls to come to an abrupt angle because it's very difficult to get heat out of those types of situations. It's also very difficult to eject the part when you have a very abrupt change in surface contour, but from a warpage standpoint, it actually influences how the surface of the part cools as well. The gate location also influences the packing effect on the part, and it also influences the flow distribution. Obviously, if you have an imbalanced gate location, or if your flow is imbalanced, then you're always going to get a difference in the flow distribution, and that will always ultimately impact how the part packs out. Because if you have one section of your part that's very far away from your gate, it's going to be difficult to get that packing effect all the way out to the furthest region from your gate location. So the gate location will always influence the packing effect ultimately, which, as we'll explore in a few moments, will also influence the volumetric shrinkage. And if we have a difference in volumetric shrinkage, again, that's where the warpage will come from. The second concept, or the second cause, is mold design. So cooling channel layout will always influence how uniformly the surface cools. That's the whole purpose of the cooling channel layout. Obviously, there's always going to be difficulties in getting cooling channels exactly where you want them because of the mechanics of the mold, because certain actions and ejector pins, slides, all these different types of actions will always influence how your cooling channel is possible, or how your cooling channel layout is possible through your mold. But the closer you can get your cooling channel system to be exactly on the surface of your part, the more uniformly your surface is going to cool down. And we'll explore in a few moments why that's important, because we actually have 2 zones of temperature that we're trying to influence. So the cooling channel layout is going to influence really what's happening on the surface of the part. and will ultimately influence your volumetric shrinkage on the surface, which will impact your final warpage of your part. Now, the placement of high thermal conductivity inserts will always allow for a more localized and conformal cooling. So where you can't place cooling channels in your mold, you can always put inserts or other types of localized cooling, things like bubblers and baffles. These types of geometries will allow for a more localized cooling, and without actually getting conformal necessarily, you can get a more localized cooling, which is pretty cool. There's a lot of innovation and a lot of different inventions coming out of the conformal cooling world, especially with the immersion of 3D printing. It makes things a lot easier to create more complex cooling systems. And like I mentioned earlier, pins and slides will always dictate where the cooling is possible. So your mold design ultimately will dictate where you can place your cooling, and your cooling placement will ultimately influence how the uniformity of material shrinkage on the surface of your part. The third impact is, or the third effect into the warpage calculation is your process conditions. The longer cycle time will typically yield more uniform shrinkage, but also makes your production more expensive. This is something that we should all be aware of. A longer cycle time doesn't necessarily always yield a more uniform shrinkage distribution and ultimately produce less warpage, but I'll say that's the general trend. So we're always trying to, through simulation and really just through molding practices in general, we're always trying to optimize the trade-off that's made between cycle time and part quality, or I'll say part consistency. All right, changing the fill speed directly impacts the shear effect and obtaining a shear balance like we looked at in the runner system earlier, and a melt cooling like we discussed earlier with the mold design will yield a balanced core temperature. So this is one of the effects that we really want to highlight, is that there's two main regions of temperature in your part. So when we're talking about filling and packing, we're impacting a lot of what's happening through the center of the part. So maybe like the 80%, I'll say, of the thickness is going to be impacted by what we call the core temperature. And that's going to be a lot of, what we looked at with shear imbalance and what we looked at with, I guess we didn't really look at it, but when we're looking at things like packing effect, we're talking more about what's happening on the core side. Whereas when we're talking about something like cooling, when we're talking about removing heat from the surface, we're talking about impacting what's happening on the surface of the part or on the skin. So the two different temperature zones are the core temperature and the skin temperature. And it's very important to kind of differentiate between those two, because our core temperature is not really going to be impacted by our cooling design, and our in the same breath, our skin temperature isn't necessarily going to be impacted by what happens in the filling and packing. Now, there is an overlap between the two at some point, but we really want to keep those two effects separated and identify which of the two we're actually trying to impact when it comes to the different types of analyses that we're running. Packing pressure and time affect the degree of packing pressure distribution, and distributing the packing pressure is important. Whereas, but there is a point where you start to overpack your part. So making sure to optimize your packing pressure and time is always going to be important in making your volumetric shrinkage distribution more uniform throughout your part. All right, the fourth effect here, polymer PVT. So PVT, or I guess the PVT relationship in general, is quite a complicated curve that isn't very straightforward. So I actually want to go through a little bit of an exercise here and show you guys exactly what our PVT does and how we use this PVT to correctly predict the trends and magnitude of warpage. So let's imagine we have a nice flat plaque here, and when we get our part out of the mold, we see that one surface is much hotter than the other surface. Given this scenario, which way do you think this part is going to warp? Is it going to warp upwards in a smiley face or downwards in a frowny face? I'll give you a few moments to think about it. All right, so the PVT relationship, PVT stands for pressure, volume, temperature. So pressure we're going to be studying the effect of pressure distribution and temperature distribution on our volume change. So our y-axis here, it's a little difficult to see, I apologize. The y-axis here is specific volume. The x-axis is temperature. And then each of these different curves represents a different pressure. In this case, we're looking at a temperature variance, but you can also do the same exact thing with pressure variance as well. So I'm going to kind of ignore the pressure effect and just look at the temperature effect for this case specifically. Now, when we're talking about a discrepancy between the surface temperatures, those different surface temperatures will correlate to different points on the x-axis. If we draw a line from those points on the x-axis up to the curve, you'll see that they correlate to different initial volumes. And that's fine. Actually, this trend is exactly what we would expect. As we heat up our part, or as we heat up the plastic, our volume increases or expands, and as we cool down our part, it shrinks down or contracts. So the colder volume is a little bit smaller initially than the hotter volume. Ultimately, we want to get the entire part down to the ejection temperature. Or, well, ultimately, you could even bring this down to room temperature. Ultimately, that's where we're heading towards. So that ejection temperature or the final temperature is going to correlate to some final volume, and ultimately we're going to get that part all the way down to the final volume for both the hot temperature and the colder temperature. The distance that we have to travel along the y-axis is going to dictate the volumetric shrinkage. So the y-axis is actually just volume. A change in the y-axis is shrinkage. So the shrinkage or change in volume for the hot material is going to be higher than the shrinkage for the colder material. Ultimately, what that means is, or the hotter material is going to pull harder or shrink more than the colder material, and that's going to cause our part to warp upwards. So that's how we use this PVT relationship, and that's really where the philosophy comes from, is being able to predict where the highest shrinkage material is going to be, where the lowest shrinkage material is going to be, and what are ultimately the differences in volumetric shrinkage, which is going to cause the warpage. Now, in this case, we just looked at surface temperature, which means that we were just looking at the skin. We could also do the same thing with the core temperature as well. If I were to look at something like a filling result, or more importantly, a packing result, because that's a little bit further on in the cycle, I could look at the core temperature and see what this effect would look like as well. The fifth effect here is going to be fiber orientation. So fiber orientation is going to really only apply to fiber-filled materials, but fiber orientation is actually a huge effect that a lot of research has gone into throughout the injection molding and other types of industries and types of molding processes. If you're not that familiar with fiber orientation, that is perfectly all right. This picture actually gives a very good idea of what the fibers actually do. If we have a high fiber orientation, let's say I call this the principal direction. If I have a high fiber orientation in my principal direction, my shrinkage is actually going to be very low, and that's because the individual fibers cannot shrink as much as the polymer. So the fibers actually reinforce the part in that direction, but unfortunately we're left with a high shrinkage in the transverse direction. So 90 degrees to my principal direction, my shrinkage is going to be extremely high. So what that means is I'm going to have a very strong part. Actually increases the rigidity of the part and the mechanical properties of the part in the fiber direction, but in the transverse direction, unfortunately, the properties are much lower. We get a higher shrinkage value, the mechanical strength is lower, and we ultimately get a less stable part in this situation where our fibers are aligned in one particular direction. Now, if you're only trying to fortify your part in one particular direction, then that's perfectly fine. But if you want a more uniform distribution of shrinkage, then you might want something like a random fiber orientation. Now, it's not very preferred to do a random fiber orientation, just because if you wanted a random fiber orientation, then you might just want to use a different polymer instead of introducing fibers and the complexities of such. What a lot of manufacturers try to do is get a major fiber orientation, but not necessarily a fully aligned fiber orientation, where maybe like 70% or close to that, 70% of the fibers will be aligned in one direction, and then the other 30% would be either in the opposite direction or maybe randomly oriented to make sure that the discrepancy between the fiber orientation direction and the opposite direction is as low as possible. So fiber orientation can very heavily influence what's happening as far as the volumetric shrinkage is concerned, and more importantly, the difference in volumetric shrinkage between the principal direction and the transverse direction. Another important note is that the weight of the fiber, or I guess the weight percentage of the fiber, can decrease the total weight of the part, which is another important aspect to why, or another important reason for why a lot of manufacturers use fiber reinforced materials, not only for the mechanical strength, but also for a weight reduction. All right, and the last effect that I'm going to go through this in a little bit more detail just because it's a little bit lesser known in the industry, is residual stress. So residual stress is created whenever plastic is molded. So there's not really a way to get around residual stress. Residual stress is essentially energy that's retained within the polymer chains that was introduced through the molding process. So as a pictorial representation of this, let's say we have some sort of like zigzag that would represent our frozen polymer chain. Once we introduce heat to that polymer chain, the polymer chain will expand or increase in length. I'll call that difference in length delta barrel. So when we're actually just going from a pelletized form in the hopper to a molten material in the barrel, we are ultimately increasing the fiber length. Now, when we actually go to mold this, we're going to apply some sort of stress to the polymer chain, and that polymer chain will actually extend a little bit further. I'll call that delta flow. So the individual polymer chains that this chain is entangled in, or maybe even just a physical pulling of this polymer chain during the process, is going to cause it to extend even further than when we went from a frozen state to a molten state. So that is going to always happen throughout the process. Then when we go from a molten plastic in our newly formed part back to a frozen material, we actually decrease, again, we shrink our polymer chain and release some of that energy out into our mold, and therefore the polymer chain shrinks in length. However, it doesn't always shrink back to its original length, and most of the time it doesn't shrink back to its original length. I'll call this delta cool between the molded polymer chain and the frozen molded polymer chain. Now, the difference between our initial frozen polymer chain and the final frozen polymer chain is what I'll call our residual displacement. So the difference between our original length and the final length is going to be the energy that is retained in our plastic after the molding process is completed. And this residual stress is actually a combination of two effects. So we have thermally induced residual stress, I'll call it TIRS or TIRS, and we have flow-induced residual stress, which I'll call FIRS. Actually, this flow-induced residual stress is exactly the delta flow. So this difference is exactly the amount of stress that's going to be retained. So the amount of flow-induced residual stress is just the difference between our molten polymer chain without any sort of external stresses and our frozen polymer chain, or I'll say the molded polymer chain, which has been stressed by some of the other molecules in our system. Now, the difference between our delta residual and this delta flow is going to be our delta thermal, or the thermally induced residual stress. And the thermally induced residual stress is really just the amount of stress that couldn't be released through shrinkage. Ultimately, if we left our part on a shelf for long enough, all of that thermally induced residual stress would be released out to the environment. And that's really why you see long-term post-mold shrinkage. So if I were to leave a part after my molding process on a shelf for, let's say, 2-3 weeks, the shape is going to gradually change. And that's because this thermally induced residual stress is being released. So this thermally induced residual stress distribution is going to heavily influence or it really is going to be a byproduct of what's happening in the warpage simulation. Any stress that can't be released by warping or by shrinking is going to be retained in the part as residual stress. All right, so let's look at what that looks like in Moldex3D, and actually just from a general standpoint, let's look at some of the best practices of Moldex3D and how we can visualize warpage. All right, and I'm going to go straight to the warpage analysis. Now, the warpage analysis is always going to be a product of the filling, packing, and ultimately the cooling analyses. And you should always analyze what's happening in the filling and packing and cooling before going to the warpage analysis. But I'm just going to zoom here for time's sake. All right, so when we go into the warpage section of our results, I'm going to go to displacement and total displacement. That's actually the result that shows up when you click on the warpage header. The color distribution that we see is actually a real representation of how much each node is moving on our part. So for example, the red nodes here are moving a lot, whereas the blue nodes here are not moving that much at all. Now, the bottom of our scale is always going to be 0 for total displacement because this total displacement color distribution is a totalization of the x, y, and z components. So we very literally take x squared plus y squared plus z squared, and that equals our total displacement squared. So very, very simple totalization, but it always means that we cannot have a negative value in our total displacement. That's actually converse to what we see in the x, y, and z. You can see that each of these can be positive and negative. Now, if I look at, let's say I just go to my x displacement, and I zoom around to the top, we can see that the nodes on the top side are blue, which means that they're moving in the negative x direction. If I look at my axes, we can see that my positive x is upwards. So all of these nodes on the top side are moving downwards. All the nodes on the bottom side are moving in the positive x direction or upwards. So that means that my part is shrinking. So that's what we should always see. There are instances actually where you overpack your part, and overpacking might cause your part to expand. And that's something that Moldex3D can predict, and it will show that if that's if that's ultimately the scenario that you've put the part into. However, in this case, we actually have a shrinkage. Now, if I go back to my total displacement plot, I can visualize this warpage very easily by going to my result tab, and this is a deformable result, so I can use the deformation function. So the deformation function will ultimately tell me, or will ultimately show me how far each of these nodes have moved based on this color plot. And I can exaggerate this warpage by going up and down in my scale. It makes it a little bit easier to visualize what's actually happening on our part. Now, obviously, this is exaggerated, but it is a good way to figure out what is actually working as far as preventing warpage and what is not working. So we can see that there's not really a whole lot of reinforcement on this feature, and there's also probably a rather large hotspot in the middle of that feature that causes all the nodes to move downwards. Now, when we're looking at the warpage results, especially the total displacement result, one thing to keep in mind is that we actually have two effects combined into this color distribution. We have the material shrinkage, or the linear shrinkage, and then we have the warpage, or the differential shrinkage. So those two effects are combined together in this result, and we actually have the ability to isolate the differential shrinkage to really see where the warpage is actually occurring. So we can actually take out the linear shrinkage from this result and only show the differential shrinkage. We do that through the compensation tool, and the compensation tool, you can either use the material shrinkage value or you can use Moldex3D's value I'm going to go through the more complicated approach and use the Moldex3D value, but you can also use an isotropic material shrinkage value as well. Those are usually pretty close to one another. To obtain what we call an anisotropic compensation percentages, we're going to go to the Warpage Log file. So if I go to Result, and then I go all the way to the right where it says Log, I'm going to drop down and go to Warpage. This will bring up our Warpage Log file. You'll see all of the different inputs to the simulation towards the top. And then your simulation will be maybe about 3/4 of the way to the bottom. Right below that is going to be your part shrinkage ratio table. So we can see in this case, our X and Z, which are transverse to our parting direction, are rather high, and then the shrinkage ratio in the parting direction is rather low. That's what you should usually see for most situations. But we can input these three values directly into our compensation plot, and that means that we can remove the linear shrinkage from our results directly. So I'm going to go back to my deformation function. I'm going to switch from isotropic to anisotropic, the difference between the two being that in isotropic, you're just assigning one single value, and it applies to all three all three axes or all three directions. Whereas an anisotropic will allow you to compensate differently in the different axes. So in this case, I have 0.41, 0.07, and 0.44. I'm going to input those directly. 0.41, 0.07, and 0.44, right? Yeah. And from this, we can actually see a little bit more clearly where our differential shrinkage is occurring. So we can see that there's not a whole lot of differential shrinkage happening over here. Most of what we were seeing is linear shrinkage, but what's happening over here is differential shrinkage, and that's usually caused by a combination of the 6 effects that we just looked at in the slides prior to coming into Moldex3D here. Now you can also export this deformed model. The deformed model coming out of Moldex3D will be an STL file. So I'll just go into this function really quick. So the model will be an STL, and I highlight that because it means that we can't get a solid model out of Moldex3D. That will come in the future eventually. It's probably in a 5-year or 10-year plan. It's difficult to know how far away it actually is, but there are softwares out there that can convert an STL over to step file, and it's only a matter of time before Moldex can do that as well. So just to note, we can export this model out from Moldex3D as an STL file. All right, so that's really all I had to say about the warpage result in general. There are a couple of other ways that we can analyze or parameterize our warpage. So I'm going to exit out of this deformation function, and I'm going to use the function right next to the deformation function called measure distance. So measure distance allows us to, well, first of all, as the function notes, it allows us to measure the distance between 2 points. But more importantly, it tells us the difference between the modeled distance and the post-warpage distance. This allows us to predict, looking at or comparing this to a maybe like a spec sheet or a parameter sheet or a tolerance. We can compare this to those and see whether our part is acceptable or not. All right, so what I'm going to do is I'm going to just measure the distance between, or measure the tolerance between our one boss here and the center of the bottom of the boss over here. So to do that, I'm going to go into measure distance. All right, it's going to ask me to select 2 points. The first point using my center snap. All right, so I'll choose 2 points on the mesh and just go from the outside of this one to the outside of this one. Save and close. And there's the table that we should get where we have the modeled distance, then the deformed distance, and ultimately the difference between them, the two, and our linear shrinkage. Mostly what we're looking for is just this deformed distance, because from a parameter sheet or from a tolerance, we're able to see whether this is within that tolerance or not. All right, and then one last thing that we can do is roundness. So roundness measurement is going to tell us how concentric a feature is after the molding process. So ultimately, we started with a circular feature. We want to make sure that that feature stays as circular as possible after the molding process. So using the roundness function, I'm just going to select any node or any point along this around this circular feature. And then I'll click Save and Close. And we see that we get an initial radius, and then we get a maximum and minimum radius, these just representing the distance, or the maximum and minimum distance from a point on this circle or a node on this feature to the middle of that, the original middle of that feature. The difference between the Rmax and Rmin is going to be your roundness. Ultimately, you want the Rmax to be as close to the Rmin as possible, so you really want this roundness to be as low as possible. And so that's a good way to gauge whether your circular features are becoming oblong, or whether your shrinkage is different in the transverse directions. So those are two nice tools that we've implemented into Studio that we didn't really have previously in the designer project workflow. Now, one of the last notes that I want to make here is that, and this is something that we found recently, and it's not necessarily groundbreaking, but it is an extremely important note. Whenever we run a warpage analysis, we always want some sort of cooling system. When we don't include a cooling system and we run a warpage analysis, and that's actually what I did with run 1 here, I ran a fill pack warpage analysis. When I run a simulation without a cooling system, we assume that the heat being dissipated from our part can be uniformly extracted from the surface. So any heat released by our part is immediately picked up by our cooling system, and that is just not a real consideration. That will never happen, and it unfortunately will lead to a discrepancy in the accuracy of your results that you get out of the warpage analysis. So what I'd like you guys to do, and this is actually a really cool feature that we have in Studio here, is we're going to use the compare tool. So the compare tool will allow us to compare the results between two simulations or two runs in the same simulation. The first thing I'm going to do is, I'm going to turn off my distance and my roundness measurements because those are just going to get in the way. So I'll just turn off my measurement section, and I'll also take off these probes as well. I'll just remove those. Right now we can see that we are looking at run 1 for both sides of our compare tool here. To switch one of these to a different run, I'm just going to highlight or click anywhere in that screen. You can see that the perspective becomes a blue color instead of the gray color. This is my active window now, and I can change this. I'm going to change this to run 2, which you can see has the title. You have to kind of hover over it, but it has the title CtFPCtW, which is our recommended transient analysis 3. Right, and I'll also go to the warpage result for that one. Now going back to my result tab, I'm going to sync the angle, and I'm also just going to sync the result between the two. So what this does is it allows me to rotate both screens at the same time, and it also ensures that I'm looking at the same result for both simulations. Now I can also, if I go back to my result tab again, I can go to sync range, which will allow me to compare these color distributions to one another. However, in this case, we can see that the difference is quite apparent in how much this part is actually warping realistically, which is what run 2 shows us. Run 2 is a real warpage analysis with a cooling system and everything. Run 1 is a warpage analysis without a cooling system, running what we call ideal cooling. So the main thing that you want to get out of this, you can actually see just looking at the maximum warpage here, you can see that we've almost doubled our warpage by running a realistic simulation. And we see this very often. This is a very common mistake by a lot of users. If you use this sort of ideal cooling scenario on the left side here, you end up under-predicting your warpage quite a bit. And then when you actually go to run this part, or when you actually go to mold this part, you see quite a discrepancy between what Moldex showed you initially and what you're actually getting out of the mold. So it's extremely important when you're running a simulation and you're trying to get a realistic expectation for what you're going to get out of the mold to run some sort of generic cooling system. And you can get as specific as you want. You can do a conformal cooling system. You can do just a bunch of straight lines to your mold base if you don't necessarily know what the cooling system looks like. From a part design standpoint, you can see I don't have any like complicated runner system or anything like that. If I'm just trying to analyze or predict the trends of my warpage, I don't necessarily need a super complicated system, but just kind of going back to I'm just going to get out of my compare tool. You can either do that by using the perspective button and double clicking on it, or you can go back to a result and just exit out of the compare by toggling it off. But if I look at my cooling system, going to the model tab, we can see that my cooling system is extremely simple. There's no complexity to this. There's no conformal nature to this. It's just a bunch of straight lines through my mold base. And from a basic standpoint, this is what you want to run a warpage analysis. And that's really the last bit of knowledge that I want to leave with you is whenever you're running a warpage analysis, include a cooling system so that you can get a realistic expectation or realistic computation for what's actually happening outside of the part. So how that heat is actually being distributed through your mold base and ultimately being picked up by your cooling system. Thank you for watching Moldex3D Advanced Tips and Tricks, and go beyond simulation with Moldex3D.